Welcome back. So today we are going to address the last version of the chi-square test. At this time, we're going to talk about the test for homogeneity of proportions. The keyword there is homogeneity. You want to know if a categorical variable is behaving the same way across many populations. That's how you recognize the test. We are going to compare at least two populations. You may remember that we addressed the two-sample z-test for proportions where we actually compared two populations only. We looked at one variable from two populations only, and we compared their proportions. This is the general case for the two-sample z-test for proportions. So in other words, you may have more than two populations, which means that if you're only addressing two populations, you have actually the option of using either the homogeneity test of proportions, or you could use the two-sample t-test. The tests are very different, but the results should be the same, okay? One more thing to mention about this is you're trying to find a difference in the distribution of a variable, a categorical variable, for many populations or treatments. They don't have to be populations. So as an example, let me just draw a little picture for you. So let's say we have three populations, okay? Population 1, population 2, population 3. So in this case, where we cannot use the two-sample z-test because that is only for two populations. And let's say we take a good sample, an SRN1, an SRS2, and SRS3. We always take samples, okay? So what we want to do is, given a particular categorical variable that we are interested in, we want to know if the variable is, if there is a difference in how the variable behaves in those populations. Of course, we only work with samples and we run a test to see if the variable is behaving differently in those three populations or is behaving the same way. That's the key, okay? So I hope you'll be able to recognize when to use this test. I think that's the hardest thing for students to do, is to recognize when you use test for homogeneity, when you use the test for goodness of fits, and there is usually one population and one categorical variable, and you want to see if it mimics the population, that particular variable. And then for the test of association, obviously you're comparing two separate populations, and you want to know if there is an association / independence or there isn't. So please recognize when to use this and when not to use this. Okay, so I'm going to work out an example. I didn't write the problem, but it's very easy for me to state. It's basically, let's say you have a very large school and high school, maybe boarding school, and it has 9th graders, 10th, 11th, and 12th. And the leadership, begins to hear, anecdotally, obviously, that these four populations are reacting differently to the food services. Okay, so we're not talking about whether people are happy or not happy. We're talking about they sense that different grades behave differently to the food services. And therefore, they took a sample from this population, and they took another sample, and another sample, and another sample. And I asked them this question. The question is, are students satisfied with the food services in these four dorms? Let's say these are dorms and they all have their own cafeteria, and they are beginning to hear different outputs or different perspectives on their happiness, level of happiness or satisfaction with the food. Okay. Now, one thing to mention, and I'm sure you know, is the samples that you take from each don't have to be equal, even if, let's say you have 1,000 people here and 1,000 and 1,000 and 1,000, even though they are all at 1,000 size in population, you don't have to take the same sample. I mean, you could, but you don't have to. So let's say from all the 9th grade dorm, they sampled 100, okay? And they asked them one by one. 78 of them said happy, 22 said they're not happy. They did same thing for the 10th grade and the 11th and the 12th. They took the same size for these two, and they took the same size for these two. Again, they don't have to be equal. And this stuff in blue is what is being recorded. People happy, not happy, not happy, and so on and so forth. Please ignore the red for now, red numbers, okay? I very quickly computed the totals, right? Totals in green are always helpful. And this is the grand total. I underlined it twice because we're going to need them to find the expected values, as you know. So right now, all that is given to me is the stuff in blue, okay? In fact, they just gave me 78 happy out of 100, so of course I can compute 22. So how do we approach this? Well, the approach is basically the same way, kind of. The first step looks very different. You may remember the two sample z-test for proportions, and what we did was we said H null would mean P1 equals P2. Isn't that what we wrote? Sometimes we wrote P1 minus P2 equals 0. That is the same, okay? And HA is exactly the opposite, or the complements. The complement of equal is not equal. Well, now we're dealing with many populations. In fact, in this case, in this example, we're dealing with 4. And how do you write it? Well, H null is obvious. It just means all the proportions from the populations are the same. What does that mean? The proportion of students satisfied with the food services is the same across all the dorms. Okay? The complements of equal does not mean, this is important, does not mean P1 is different from P2, is different from P3, is different from P4, right? The complement of equal means at least 2 of them are not equal. At least 2 dorms have different perspectives on their satisfaction with the food services. The way you write it mathematically for the equal, you say PI, this is just a dummy little letter, subscripts, PI equals PJ for all, the keyword is all, for all I and J. P3 is P4, and P1 is P2, and P1 is P4, and P3 is P2, and all of them are equal, okay? At least 2 of them are different. It means PI is not PJ for some. Doesn't mean for all, just it means for some. So it's possible to have P1 equals P2 equals P3, but they're all different from P4. Or P1 is P2 and P3 is P4, but these 2 are not the same as these 2. Makes sense? So this is how you would write it mathematically, or you could just put it in words, okay? The next thing, of course, is the testing the conditions. The randomness, of course, we want to make sure that when somebody want to take the opinion of the 9th graders, and who knows, maybe there is 1,000 students total, how did I pick this 100? Okay, so let's say there is 1,000 students in the population of 9th graders in that dorm. How were those 100 picked? Not how these were picked. These were questioned based on 100. So once they settle on a sample, they simply ask them, are you happy or not happy with the food? If you're happy, we count you here. If you're not happy, we count you here. We're addressing in this question, we're addressing the green number. So is it that in the basement of that dorm, there were 100 kids hanging out watching a movie, and they asked them if that is the case, that sample does not represent the population of all ninth graders. Let's say there are 1,000, okay? So we want to make sure that these 4 samples are taken properly, which simply means that they represent the population of interest. I'll write it down. Make sure that the samples represent the population in population. So we're talking about which population? Well, for all 4 populations, right? Okay. The large counts, if you remember, was we want to make sure all expected values are more than 5. So I'm jumping the gun here. I already did the math, and we're going to go back to how we got these quickly. So you would have to find the expected values before you can answer this question. Of course, you could just say, according to my expected values, all numbers are more than 5. Oops. All expected values found. Don't just say there are more than 5 without verifying. Found are greater than 5. And finally, the 10% condition. Okay, so if these students were interviewed with replacements, then you don't need to verify the third condition. We're assuming that once they ask a student, that student is no more in the pool, is no longer in the pool. In other words, let's say those students are in the basements and they represent the population of interest, okay? And it's a really good sample. And they ask the first person, are you satisfied or not satisfied? And no matter what he or she says, that person generally is not asked again. Pretend that they leave the room, they're gone. So that is without replacements, right? And whenever you're selecting without replacements, you must check the 10% condition. Basically, we want the population size to be very large. So if the population of 9th grade dorm is at least 1,000, at least 750, and at least 750, then you're fine. If the population size is smaller than the numbers I just mentioned, 1,000, 750, 750, then we have problem unless those kids, whether or not they're asked, they're back into the pool of 100. They don't leave the room. They're still there, and it is possible that somebody asked them again the second time and the third time, okay? So just make sure you clearly states, assume the populations are at least 1,000, 750, and 750 respectively. Respectively simply means this is representing 9th grade, 10th grade, 11th grade, 12th grade, okay? So if I say I am, and you are 50 and 30 years old, it means I am 50 and you are 30. That's what respectively in mathematics means, okay? So we'll go to the calculation. So before we find the chi-squared, we need to know the expected values. And this is what I did here. And remember how to find the expected value. We know out of the 9th graders, out of the 100 9th graders, 78 of them said that they're happy. To find what you expect to get, you multiply this total by this total, and you divide by the grand total. So if you multiply this by this, divide by that, you get this number. Notice these two are the same, even though these two are not the same, because the 100 didn't change, and the 243 didn't change, and the grand total didn't change. So what we expect has nothing to do with it has to do with the number, but even though these are different, these expected values turn out to be the same because the grand total was the same. Okay, same thing here. These two turn out to be the same because 75 didn't change. Okay, and 243 of course didn't change, and therefore the 350 didn't change. So that's how you get the red ones very quickly. Call the expected value, and all you have to do is take the observed minus the expected squared over the expected, and then you add them up. Of course, you don't want to do this by hand. It takes a long time because what you would have to do is take this minus this, square the whole thing, divide by that, plus this minus this, square over that, and go through all of 8 of them. This minus this squared over that. Once you compute that, you're gonna get a chi-squared here, a chi-squared, a chi-squared, a chi-squared, and then you have to add all of them, right? You have to add all of them. You have to add all of the values, and that's what I got, and I'll show you how to do it again. I know we did this before, but I'll show you how to do this quickly, okay? Degrees of freedom here is, we're comparing 4 populations, so it's 4 minus 1 is 3. You can also do a 3 by 2, if you think about it. This is a 4 by 2, and let me write it here. Row minus 1 times column minus 1, which is 4 minus 1 times column minus 1, which is 3, right? So that's how we got this 3. We know 4 proportions, or 4 populations. I should have said 4 populations, okay? So this, the last thing we do on the calculation piece is we find the p-value, which is the probability that that chi-squared is over this, okay? And you go to distribution, chi-squared CDF, and you write your interval from 8.4569 to some giant number, and then you insert the degrees of freedom, and I got 0.037. Just to remind you, the chi-squared looks like this, right? And here is the chi-squared we found, which is 8.4569, and we are trying to find this area called the p-value. That's all we're doing. So the probability that chi-squared is more than this, and you've got to recognize degrees of freedom to find the p-value. So if we use a significance level of 0.05, clearly 0.03 is less than 0.05. Therefore, we are willing to reject H null. If we reject H null, we're saying that at least 2 dorms have a different opinion in their satisfaction with the food services. And that's all I wrote here. We can conclude that at least 2 dorms differ in terms of the proportion of students satisfied with the food services. Now, to go back here, just quickly remind you how to do this. What you do is you go to stat edits, and under L1 you put all the 8 observed values, right? The satisfied and the non-satisfied, and you write their corresponding expected values. So you cannot mix that with that, for instance. So that goes with that, and that goes with that, and so on and so forth. In other words, when you write this under L1, you write this under L2 right next to it. So now you have 8 values on each column, and what you want to do is find L3. L3 is just this quantity without the sum, okay? So what you have to do is take your L1, subtract your L2, square the whole thing, and divide by L2. And that's all I did here. So you go to L1 like this. This is L3, right? You've got to go all the way here. Don't stay here. It's not going to do it for you. You've got to go all the way here, click on it, and then type L1 in parentheses minus L2 squared, divide by L2. And that should give you a column L3, which are all of those values. So you'll get 8 of them. And what do we want to do? Of course, here we need to add them up. And there are 2 ways to add them up. So the chi-squared value is the sum of L3, obviously. And that's how I got this number, okay, which has been used. And there are a couple of ways to do it. One is to go to stats, calc, one var stats, okay? And then you look for the sum of x. Now, what does the sum of x mean? It means the sum of L3, because the window, once you go to one var stats, you want to click on L3, okay? And you calculate, because you want to add L3. You're not trying to add these. You're trying to add L3, right? So make sure this is L3. I think it'll be there for you because that's the last thing you did. If not, make sure you write L3, click on calculate, and you, out of the menu, you pick the sum of x. What is that x? That is L3. That's the variable. So that's one way to do it. A quicker way to do it is to go to second stat, which is list. You go basically to list, go to the right to math, and then number 5 is called sum. On the home screen, you'll see the word sum after you click on it. Make sure you start with the home screen first, okay? And you enter L3, and it will give you the sum, okay? That's how you get this, which allows you to find the p-value, which allows you to compare the p-value to alpha, which allows you to draw a conclusion in the context of the problem. Once again, my friends, the hardest thing to do is to know what test to use. Most students have no trouble going through step 2, step 3, and step 4. What you might have trouble with is recognizing that this is a chi-square test, number 1. Number 2, it is a test for homogeneity of proportions. It is not test for goodness of fit, and clearly we're not trying to compare 2 variables here to see if there is an association or not, okay? I hope this was helpful. It serves as a nice reminder of the other 2. And till then, have a good one.